Hello everyone, let's analyze. So the oft asked question, why did the chicken cross the road, is not really the question a mathematician should concern themselves with, but rather, did the chicken cross the road? Let's leave the why to the chicken psychologists of the world. Well, if the chicken was on one side of the road and is now on the other, we can conclude that at some point the chicken was on the road as he crossed it. His motivation for crossing remaining a mystery to the universe. We can conclude that he was on the road by applying the intermediate value theorem, which, in spite of its lofty name, is just a bit of common sense wrapped up in mathematical rigor. In fact, continuity was well understood for quite some time before Bolzano came across and rigorously proved the result. Not because he was the first able to, but because he was the first that thought that the question should be treated with such rigor. To mathematicians before and of his time, the idea just seemed too obvious. But we do have the tools to prove the result rigorously. So we'll continue. We'll continue with the theorem that Bolzano did prove, which we can think as a precursor to the modern intermediate value theorem that we think about, but is really, as we'll see shortly, equivalent to. Suppose f is defined on a closed interval and is continuous. And suppose that f of a is negative and f of b is positive, a and b being the left and right ends of the interval, which is the domain of f. Then there exists some c value in the domain for which f of c is 0. Of course, we call c a root of the function f. So let's prove the result. We're going to start by defining a subset of the domain S as all x in the domain for which the function is not positive. In other words, less than or equal to 0. So you see there illustrated an example of a function and an example of this S set highlighted in red. And you can see it's a subset of the interval a to b. We know S isn't empty because, well, A is an S. We know it's bounded because it's inside of the domain. So the least upper bound axiom tells us that a supremum exists. Let's name the supremum C. Now, the trichotomy axiom tells us that, well, f of c, and by the way, f of c is defined because C is the supremum of S, right? Which means C is either in S or is an accumulation point of S. And because S is in the interval a to b, C is in the interval a to b. Therefore, I can actually make sense of what f of c is. So f of c is negative, 0, or positive. So let's investigate each possibility carefully. Suppose that f of c is positive. We know that there exists a delta neighborhood of c for which f of x is also positive for all x in the neighborhood and domain. We know that from homework 9, problem 4. But we also know from the equivalent definition of supremum that there exists an x in the set for which c is a supremum of, that is S, such that x is greater than c minus delta, but less than or equal to c. Now remember, what does it mean for x to be in the subset S? It means that f of x is not positive. But we said that f is positive for the delta neighborhood. Well, if x is less than or equal to c, but greater than c minus delta, then x is in the delta neighborhood, for which we're saying f of x is positive. It's specifically on the left side of the delta neighborhood. So the fact that x is in the neighborhood for which f of x is positive, but x is in S, meaning that f of x is not positive, gives us a contradiction. So it's not possible that f of c is positive. It must be not positive. Okay, if it's not positive, it's either negative or 0. Suppose it's negative. Well, for the same reasoning behind your answer to problem 4 of homework 9, there exists another delta neighborhood. We'll call it a delta prime neighborhood of C, for which f of x is negative for every x in the neighborhood and domain. Now suppose x is one of those values in the right side of that neighborhood where f of x is negative. Now if x is in the right side of the neighborhood, that means it's greater than c, but less than c plus delta prime. Now remember, we said in this neighborhood f of x is negative. That means x would be in the set S and greater than c. Well, that can't be, because if x is in S and greater than c, c can't be an upper bound for S. But remember, c is by its very definition an upper bound. So it's not possible that f of c is less than 0. Well, the only remaining possibility is that f of c equals 0. And we've proven our result. And in fact, this result will yield the intermediate value theorem. Suppose f maps a closed interval, a to b, to R, and f is continuous. Well, if k is any value between f of a and f of b, right, if f of a is less than f of b, then k is greater than f of a but less than f of b. And if f of a is greater than f of b, then f of a is greater than k, which is greater than f of b. In other words, it's in between. Then there exists a c in the domain for which f of c equals k. Now I claim that the proof of this follows very directly from Bolzano's theorem previously. Of course, you might say, well, how is that? Because the previous theorem dealt with roots, and this is dealing with a function equal to some k. Well, simply let g be f of x minus k. If g is f of x minus k, a root of g, let's say c, let's say g of c equals 0, that means f of c minus k equals 0, implying f of c equals k. So all we got to show is that g of x has a root. And the fact that g of x has a root follows from the previous problem. Suppose we're in the first case that f of a is less than f of b. Well, then g of a is less than g of b. Furthermore, we know that g is continuous because it's the sum of two continuous functions. F is continuous, and negative k is a constant function, so it's continuous. Therefore, the previous theorem directly implies that there exists a c in the domain for which g of c equals 0. Meaning at that same point c, f of c equals k. Of course, we've only proved the result for when f of a is less than f of b, but the result follows in the same way for when f of b is less than f of a. We just take the function g of x equals k minus f of x. Again, g is continuous, g of a is less than 0, g of b is greater than 0, therefore g has a root c, in other words, a value for which g of c equals 0, meaning f of c equals k. And we've proven our result. So let's give a few examples of how one might apply the intermediate value theorem. Let f be the following fifth-order polynomial, x to the fifth minus 5x plus 3. Prove f has a root on the interval 1 to 10. Well, we know all polynomials are continuous. In fact, you know it very well because you proved it in the homework. Well, f of 1 is negative. F of 2 is positive. In fact, f of 2 is 25. That means there exists a value between 1 and 2, which is contained in the domain 1 to 10, for which f of c equals 0. Now, note here that the power of the intermediate value theorem only goes so far. We know a root exists, but not yet what it is. However, the idea behind the intermediate value theorem actually suggests a very powerful algorithmic tool for approximating roots. We know there's a root between 1 and 2, so we could just have the interval from 1 to 2 to figure out which of those two halves is guaranteed to contain a root. Find the half that's guaranteed to contain a root and then half that interval again. Of my two new intervals, find which one has a root and halve it again. The length of my intervals of each interval at iteration k is, well, the original interval divided by 2 to the k, which gets small fairly fast. So we can actually use that as an algorithm for not only finding a root, but guaranteeing that we have lower and upper limits of where a root has to be. Now explain why the equation cosine of x equals x must have a solution in the interval 0 to pi over 2. Now, the algorithm I just described of taking an interval guaranteed to have a root and halving it, finding which of those intervals is guaranteed to have a root, and then halving it and continuing until you get close enough to a root to stop, is what's called a root finding algorithm. And this specific algorithm is what's known as the bisection algorithm. We could actually apply that same idea to cosine of x equals x. Now, of course, looking at it, you might say, well, wait a second. Finding a root means finding which value of a function makes the function 0. But here I have an equation, cosine of x equals x. Well, if I just take all my players and put them on one side of the equality, then solving the equation becomes equivalent to finding a root. Let f of x be cosine of x minus x. Then wherever f has a root, cosine of x minus x is 0, implying cosine of x equals x at that value, at the root. F of 0 is cosine of 0, which is 1 minus 0. And f of pi over 2 is 0 minus pi over 2, which is negative. So since f of 0 is positive and f of pi over 2 is negative, as f goes from 1 to negative pi over 2, at some point it crossed 0, meaning there's some c in the interval 0 to pi over 2, for which f of c equals 0, implying cosine of c equals c. Here we have some pictures illustrating the result. On the left, we have a plot of cosine of x and x. We can see that they do intersect. On the right, we have a plot of cosine of x minus x. We can see that it clearly has a root. Not only that, the two functions intersect at the same point that their difference has a root. Now a quick word about the history of the intermediate value theorem that I alluded to earlier. The theorem was first proved in 1817 by Bernard Bolzano. Cauchy gave a proof several years later. Now, you can actually read more about the history of the intermediate value theorem and its connection to the French Revolution. Because if you're going to fight, the intermediate value theorem is definitely worth fighting for. Now, if you want to know how the intermediate value theorem and the French Revolution are connected, then you should read the paper Stuck in the Middle, Cauchy's Intermediate Value Theorem and the History of Analytic Rigor by Michael Barony, published in the Notices of the AMS, Volume 60, Number 10, and published in 2013. And by the way, if you'd like to get your hands on that article, you can just click that blue part. It's a hyperlink. Included in the paper is the following quote. At first glance, the theorem seems obvious. Indeed, generations of mathematicians before Cauchy thought its idea so obvious as to not to need explicit statement or justification. On the other hand, that the theorem can be proved with just some simple notions about continuity, convergence, and the system of real numbers is something quite remarkable. Students learn to take nothing for granted, to proceed systematically, and to use approximations and limiting principles to turn vague intuitions about the nature of functions into indubitable theorems. Michael J. Barony. That's all for today.